Good afternoon, good evening, ladies and gentlemen. Welcome to another series of online tutorials with me, Aubrey. If you haven't already, please subscribe to the channel, leave a like, comment, and share. All right, so in today's lesson, we are looking at a tutorial. This was an assignment given to the Masters of Science in Mathematics. This is mathematical statistics. This is just simple assignment. So assignment 1, question 1 asks to show that x has a Poisson distribution if y has a Poisson distribution and x given y equals to y has a binomial distribution. All right, so we have y, let me write this, y has a Poisson distribution with parameter that, then x given y has a binomial distribution with parameters that. Okay, so now to show that x has a Poisson distribution, we'll try to find the probability of x. Okay, so the probability of x is just the sum of all the probabilities of x. All right, the other way we can write this, if we were to include this information that is here, we can write this as the sum from 0 to infinity of probability of x given y equals to y times the probability of y equals to y. So this is the same. This is the condition probability rule. So the idea is that the probability of y and the probability of given y can cancel out and you remain with the probability of x, which is just this. Is the plot behind here. So we can do that. So for this one, we have probability of x given y, which is a binomial distribution. So for binomial distribution, the probability of x given y for a binomial distribution that is given by y choose x, then p to the x. Then for y being a Poisson distribution, the probability of y is just equals to lambda to the y over y factorial times e to the negative lambda. So that is the information that we need. So we can rewrite everything and replace in this formula here. So this will finally be equal to the sum from 0 to infinity. Then the probability of x given y is a binomial distribution given by y choose x, p to the x, q to the y minus x, times the probability of y, which is a Poisson distribution. So the Poisson distribution is given by this, for y factorial, then e to the negative lambda. All right, we can start simplifying things. So this can be written as the sum from 0 to infinity of y factorial all over x factorial times y minus x factorial. Then we have p to the x, q to the y minus x. Then this part, for us to have y minus x, we can write it as lambda to the y minus x. Then for us not to change anything, we multiply by lambda to the x, so that since they have same bases, when the powers are added, we will revert back to that. Then we have over y factorial, then e to the negative lambda there. All right, so we can start simplifying things. We see that this and that can go. Then we can group these that have the same powers. We see that this and that have the same power, and this and that have the same power. We can group them together so that we have the sum from 0 to infinity over p and lambda x can be grouped. Then we factor out the power x. Then q and this can be grouped together. So q lambda to the y minus x, then all over x factorial times y minus x factorial, then times e to the negative lambda. So what we'll do here is we will factor out lambda p, because it's what we're looking for here. Lambda p or p lambda, that is what we're looking for. So we'll factor out this. So since this has a power x, we can factor out this that has a power that is x factorial. Then we also factor out e. Then what we're going to remain with is equal to, so we factor out this can be written as lambda p to the x. We also factor out e to the negative lambda and x factorial. Then what we remain with is the sum from 0 to infinity of q lambda to the power y minus x all over y minus x factorial. Okay, now we need to look at this part that is here, and we know from experience that this is gotten from we can find the function of this, or the Maclaurin series expansion of this. So we can say, but the Maclaurin series of e to the x is just equals to the sum from 0 to infinity of x factorial over, of x to the power n, of x to the power n all over n factorial. So you can prove this one and you can look it up. So we see that what is here is representing more like x, and y minus x is representing n. So what we just have is x is this x, so we can transform this. We can say probability of x equals to x will be equal to, we have what we have here, the p to the x e to the negative lambda over x factorial. Then this now changes to e to the lambda q. So we are just following this. This is this, so this will be to the power that. So that will be the relationship there. Then we can now simplify. So now we are going to have, we can add the powers since the bases are the same. So lambda p to the x e to the negative, we can say lambda plus lambda q all over x factorial. Then this will be lambda p to the x. We can factor out negative lambda on top. We remain with 1 minus q all over x factorial. But we know that 1 minus p is equals to q, or p is equals to 1 minus q. All right, so we know this. So here we can replace with p, so that what we get is lambda p to the x, then e to the negative lambda, then this becomes p all over x factorial. And we see that this is actually a Poisson distribution. with parameters lambda p. All right, so that is what you're supposed to do for the first part. So we see that x has a Poisson distribution with parameter lambda p. So that is our first question. Then in the next video, we'll look at the second question right here.